Welcome you to today's video lecture. Today we will continue time response, and last time we discussed in previous video about what is poles. Zeros and poles are actually denominators of the transfer function. Zeros are the numerator roots of the transfer function. So if you find the roots for numerator and denominator, from there you can get poles and zeros. Now from the start we discuss first order systems, and first order system we define which has only single pole. Now if we look at this is an example where we discuss that we have a transfer function with 1 0 and 1 pole, and we just write in on S plane with real axis and imaginary axis. 0 is plotted by a circle and poles by the cross. Okay, so how we calculate it? For this transfer function we put s plus 2 equal to 0, we get 0. For root we calculate the root, and that becomes minus 2 and that becomes 0, and similarly 5 plus s plus 5 equal to 0, s and minus 5 becomes a pole, and we just plug in here. Now we represent pole by cross and 0 by circle. Now for time response, because response is also known as your output, so a transfer function, as you know, that is the ratio of output to input. Now to calculate the response or output, what we have to do, we have to write the frequency response of the output. That becomes C of S, that is transfer function multiplied by the input. Now after that what we have to do, because we want in time response, so we need to calculate the inverse Laplace. So for inverse Laplace we do the partial fraction, and from here we get the inverse Laplace. Now using the Laplace table we get this response. So for that response we normally do need the input. Here we get the step input to the system. Now if we look at this is the response due to the input, and this is because of the transfer function. So this is known as your natural response, and this is also known as forced response. Now if you plot it, this is what you get, and you easily calculate this, but putting t equal to 0 you get this point, t equal to infinity you get this point, and you know that this is exponential decay. Just make a decay and you easily plot the response. Now if we move further and look at the properties of the first order system, for that case what we did, we get a very standard form, and we wrote a standard form, that is A divided by S plus A. Okay, so this is the standard transfer function of a first order system. Now we are interested in the response, so that why we write the C of S, that is the output of the system. Now output of the system is input times the transfer function. Now you have to note that because we cannot proceed this further until we have to solve this and decided what is the input to the system. Now the standard input that we use in control system for analysis is the step input, that is you just switch on and for a time duration, okay, with some magnitude. So here RFS we use as step input, that if you look at the Laplace of step, that is 1 over s. Now I plug in here and I get this as the output. Now I told you that you have to do the inverse Laplace so that you can look at the time response. Okay, so for time response what we did, we just do the partial fraction and we get this result. Now here we have one that is because of the forced response, and the other is known as natural response, that is the exponential. Now this is the result for first order inverse Laplace. Now we have some properties of first order system. The first one is known as time constant. Time constant is defined as when your response, the final value, reach the 63% of it. For example, in our example, final value is 1 and 63% of 1 is 0.63. Now if I put in this equation 0.63 and try to find the time, and that time come out is known as time constant. Now when I do the calculations, I get the time constant equal to 1 over 8. That means that time constant is actually equal to the inverse of the pole location. So this is your one of the way that if a pole is at minus a, you just take the magnitude. So this is known as time constant, normally represented by the tau. The next thing that we can calculate is known as rise time. Rise time is the time that your system get 10% to 90% of the final value. So the time between 10 to 90% known as rise time. So if I put 10%, similarly as I put 0.63 equal to this relation, I get this value, that is 2.31 divided by a for 10%, then minus sorry, for 90%, then minus for 10% I get 0.11 divided by a. So I minus this thing because I need time between them, so it becomes 2.2 divided by a. So this means that if you have a first order system, for that case your rise time is 2.2 divided by pole value, location of the pole. Okay, so look here, this is the response. We are reaching 1, but we didn't reach it. It took infinity to reach. If I plug in, if I wrote the equation, that is 1 minus exponential minus 80, so for t equal to infinity we get the 1, so that's why it is trying to reach the 1, and 1 is this the line. Now again, now look here, if I calculate it, this is the time, okay, rise time. The last thing is the third one in first order. The property is known as settling time. Settling time is 4 divided by a. So you can easily calculate it when your time response reaches a stay within 2% of its final value. So in same relation, if you put 0.98 equal to 1 minus exponential minus 80 and you calculate the time, that time is known as steady state time. So if I do that, look here, so this is your steady state time, so it is from 0 to this time. Okay, so there are three basic things that we discuss for first order system. One is known as time constant, second is rise time, third is steady state time. Now we move to next and we discuss because this is there are two. I told you that normally we divide response into basically two basic parts. First is known as first order and second is known as second order response. So today we discuss second order system. So how we define a second order system? Of course, second order system has at least two poles. Okay, okay, a second order system has two poles. This is one thing, and second is it exhibits a wide range of responses that must be analyzed and described. Okay, in first order system, parameters simply change the speed of the response. Changing the parameter of second order system can change the form of the response. Okay, so first order system parameter change the speed of the response. Okay. In second order, parameters change the form of the response. So if you remember, in first order system we discussed the time constant, rise time and steady state time. So if you increase or decrease the value of a, u or pole, it will change. But in second order system this is not the case. We will discuss it in very detail today. So how this happens. So now it's better to start with looking at the poles and zeros of the system. So normally for second order system, how block diagram look like. So if I want to write a standard form, so we have S square, that means that you are talking about second order system plus B. So this is your G of S, and again we have R of S, that is the input, and we have C of S, that is the output. Now I told you that normally we give step input as a analysis input to the system and see how system performs. Okay, so this is second order system because we have this term tell us that this is second order because S square, so this means that you have two poles in it. Now if I move to responses, what type of responses we have. So first one, if we look, is if it is 9 divided by S square plus 9s plus 9. Okay. So this is the first G of S. So for this system, if I plot the pole 0 plot, okay, so this is your S plane, this is known as right hand side, this is known as left hand side. Okay, so this is your real axis, this is your imaginary axis. Okay, now if I calculate the roots for this, so roots come out to be, first one is 1.146 and second one is minus 7.854. So you know how to calculate the roots. If I go back for this equation, so roots calculated is equal to minus a plus minus a square minus 4b divided by 2. Okay. So this is the relation from where you can calculate the roots value. So if we use same formula, we get this thing. Now for here, look here, these are both in negative, so exponential is decaying. So if we give step input to the system, okay, so for that particular system, so this is your step input, this is 1. Okay, now how response look like. It will start from 0 and trying to reach so it will start from 0 and trying to reach the this is the response. All right. Now the okay. Now the response is trying to reach the one. Okay. So if I look at, this is your C of t and this is your t. Okay. So let me change the pen settings so that it's much clear. So this is your C of t. This is your t. This is your response. That's much better. Okay. So if I write the formula, so here C of t is equal to 1 minus, okay, 1 is for what you say, force response, minus 0.171 exponential minus 7.854 t, okay, minus 1.171 exponential minus 1.146 t. So this is the response. So we plot it. So if you look at it will not cross the 1. If response is not crossing the 1, so that response is also known as overdamped. So this is a response that is not crossing 1 is known as overdamped response. So if we look at the second transfer function, that is g of s is equal to 9 divided by s square plus 2s plus 9. So if I calculate the roots for this one, so these roots become complex values, okay, but with negative sign, means that in decaying side, so means they are stable. So if roots are on the left hand side, we call it system is stable. Why? Because it will start decaying. It's not going to increase. Why? Because this is the power in exponential. If exponential is in negative sign, so this means that it shows that time response is decaying. When exponential power is positive, so it means that it is growing. When something is growing, so this means that that thing is unstable. When something is decaying, so this means that energy is removing from the system, so that system is going towards stability. Now here response is a complex value, so complex values are, for example, this is your minus j8 and this is your j8, so and this is your minus 1, so the value here is minus 1 plus j8. Similarly here value is minus 1 minus j8. So this is the root values. So whenever you have this type of values, so in that case we do have some, when we give input to the system as a step input, so the response is look like this. Let me draw the response here. Okay, so again, if this is my 1 and my response equation look like C of t is equal to 1 minus exponential minus t times cos of under root 8t, and I think we have plus here, under root 8 divided by 8 sine of under root 8t. So this means that there is some overshoot is involving in it. So let me change the now it will start from here and give some overshoot and then try to settle them. This is the response when we have poles at complex poles. So this has overshoot, okay, so this is overshoot come into the system and it has oscillation in it. So this is the oscillation. So this type of system we call it as under damped system. So over dam means that you can't cross one, under dam means that you crossing the one, so means that they are under damped. Okay, now start from here. I didn't plot to make the equation visible, so let me plot it here and rewrite the equation. So it's better to rewrite the equation. So C of t is equal to 1 minus exponential minus t times cos of phi of t plus under root 8 divided by 8 sine of under root 8t. So this is the response. So when you have this type of response, we call it as underdamped response. Now if we look at the third one, now we will move to next page. We have very less space here. So on next page we look at the third response, that is we have this transfer function. So transfer function is 9 divided by s square plus 9, and you have r of s, this is your g of s, and r of s is step input and c of s your output. So if I plot the j omega axis, now look here. So if I solve this, this becomes 3j and minus 3j. So this is the location of the poles, and now pole's location is on the j omega axis. When pole location is on the j omega axis, so this means that it will oscillate, so it is known as undamped response. So it will start oscillation. So if I draw the so if this is your 1 and this is your 2, so this is your 0 and this is your c of t. So it will start from here and it will start from here, go up to 2, then come back, then go up to 2. It will start oscillations like this. Okay. So if I try to write the equation for this, this becomes c of t is become 1 minus cos of 3t. So this means that it is 1 minus cos of 3t. So this is the oscillation that you can get. So if you have pure oscillation, so that response is known as undamped response. Now the last one that we are interested is is 9 divided by s square plus 6s plus 9 g of s again R of S, and given input is the step input and C of S is the output. So this is the response when we have a roots both lie on the same point, that is -3. Okay, this is in my S plane, this is my j omega axis, this is my real axis. So this is known as critical damped. So this is a very ideal result that we actually want in control system, known as critical damp. So this is my CFT. So if this is my 1, okay, critical damp means you start from here, you will reach 1. So this is known as, this response is known as critical damp. So the relation of critical damp is 1 minus 1 is because of the step input 3 exponential minus 3t and minus, sorry, there's a t as well because repeating root, so we have minus exponential minus 3t. So this is known as critical damp response. Okay, so these are 4 possible response. Fifth one is unstable. We are not interested in unstable. Now if we look at, we just discussed all those responses that lies either on the j omega axis or on the left hand side. So this means that we are interested in stable system response. So if we review what we discussed, if we say that type of response, then we say roots. Now first one is hour damped. Okay, so for hour damp we have 2 distinct left half plane roots. Second one is we discussed was underdamp. So for underdamp we have 2 complex roots, 2 complex left half plane roots. Be careful to saying left half plane, that we are discussing a stable one. Third one is undamped. For undamped we have 2 j omega no, not say j omega, say complex on j omega, complex j omega axis roots. So then is undamped, and last one is a critical damp. So for critical damp, 2 repeating left half plane roots. Okay, so this is what we have. Now in first response, it is reached at infinity to the, what you say, 1. It will cross the 1. Okay, so undamp is actually oscillating, and critical damp is that it will reach within time, so there is no overshoots. Okay, so so if I this is what we have. Now we will move to next one, and we will look at how we get these responses. So what we are doing here is that we have second order system, okay, and we are interested in looking at if this is my 1, okay, and this is my response, alright. So this is my t-axis and this is my time, okay. So if I look at different responses, and so one can be have, for example, this is 2, alright, can have this type of response. So this is undamped response. For undamped response means that you have complex j omega axis poles, okay. Then we have critical damped response. This is critical damped response. Then we have I just want to plot all on one axis so that we will look at what is the difference. Then we have this one is our damped response. Then we have then we also have underdamped response, that is doing like this. This is underdamped. So these are possible response when we have stable system. We can say that a system that has poles on the j omega axis or on the left side of the j omega axis. Now before going further, what we can do here is if I change this color as a green, so that it will highlight it further better, okay. Now how this response and pole location behave. Now if we move to next and this is my S-plane. So this is your real part, this is your imaginary part. So this is 0. So here you are in positive values, here you are in negative values. So for example, we have 1, 2, 3, 4, 5. You have -1, -2, -3, -4, and -5. Okay. So similarly, you have negative values here. -j omega, -2j omega, -3j omega, so on. Similarly, you have j omega, 2j omega, 3j omega, and so on. So this is my S-plane, and we call this part as right hand side at right hand plane, and this is left of plane. So this is left of plane, and we call it as a imaginary axis. Okay. So here actually if you just work on this j omega axis, normally this means that you actually if you work on this axis only, so this means that you actually doing Fourier transform where s is equal to j omega. Okay. So but we are doing both one, and then this means that you are actually doing the Laplace transform. Now let's see how poles behave. Okay, so for that case we know that if we have 1 over s, so if we look at the inverse Laplace of 1 over s is 1. Similarly, if I have 1 over s plus a, so Laplace is exponential minus at, so it depends upon. So this is the basic idea that we can get from Laplace transform. Now if we have a pole at the 0, so this means that this has response like this because of the 1. Okay. So if we move on the top, so if we move on above or below, then we have 2. Then we have pairs of poles. Okay. Now let me change the color, make it green, so that people will understand. Not green is not good. Okay. So if we move above, we are in pairs. So for these pairs, how response look like? For if you have a pairs, then in that case response look like oscillatory response. Okay. Now if we move on real axis only in one direction, that is in the right direction. For example, if we are here, because this give us exponential 3t, and you know that exponential 3t is growing, so in that case response will be will start growing instead of decaying. Okay. So it will start growing. So it will start growing like this. Okay. So if we move further, for example, if I am here, this growth is a rapid one, means that you have much faster growth you will find in the response as you move further away from the origin. So this is my origin. If I move further away from the right side or left side, my response is fast. If I am at the right side, so this means that response is growing fast. Similarly, if I move on the left side, for example here, now my response is decaying. Okay, we expand minus 2t. But if I go further here, this decay is fast. Sorry, let me rewrite. So what do you mean by fast? Fast means that it will quickly decays as compared to this. If I move in this one, so response is fast. Again, fast. So if I go move further away from the origin, response is fast in both directions. What we also move on the what you say, if I move further away in this direction, so frequency increases, means that, for example, if I am here, so oscillation frequency is increasing. like this as compared to this. So if I move further on above or below on the j omega axis, frequency of the response increases. So this means that as we are near the origin, we have very what you say, response is very slow, but as we go away from the origin in any direction, response is fast. Now let's see important, if we have a pair on the left side, so in that case we have a response, okay. So because it has this part, that is decaying part, also the oscillatory part, so it contains two. Because of the decaying, it will start from here and try to decay like this. Okay. Now if I draw a dotted line, this dotted line is the envelope, that is because of the value here on the real axis, and this response is because of the value here. So this is oscillation because of this, and this envelope is because of this value on the real axis. So imaginary axis give us the how oscillation behaves, what is the frequency of decaying, and how fast it decays is because of the real axis. Okay. So similarly, if I go further here, for example here, how response look like, it will further fast, so means that it will start fast decaying further like this. So because of this envelope, that is value on the real axis, that make it fast decaying. So similarly, if I am here, so it will start growing in that direction, so it will start growing like that. Okay. So if I go further, or if I go here near to this, so it will grow, but grow is a bit slow like this. Okay. So the main idea is that this grow is because of this envelope, that make it to grow or converge or diverge is because the real axis, and this frequency is because the imaginary. So this is the main idea. Now from here we have a concept, that is, if we are more toward the real axis or origin, so means that the response is slow, or means that the response that will stay for longer time. If we go away, it will die down very quickly. So this is the response that we are getting when we are having second order poles. How response will behave. Now I will stop here.